Next, we're going to talk about the very cool phenomenon of the photoelectric effect. And what this means is that we're going to shine light waves on a metal and then electrons leave. So what gives? Where are the electrons coming from? How does the light make the electrons leave? And this is called the photoelectric effect. And the emitted electrons are called then photoelectrons, another creative name. This was first discovered by Hertz in the late 1800s, but we didn't get an explanation until Einstein, who won a Nobel Prize for it in 1921. The classic theory predicted that, okay, so light on, electrons off, cool. So the classic theory said we should be able to shine any light, that we should be able to shine red light, blue light, that it should give us electrons, just maybe fewer. So light with more energy will cause the electrons to be ejected with more energy. So this has to do with like intensity. So if we turn up, if we have a really bright red light, it should eject electrons with more energy than a blue light because it has more energy. So the rate that electrons will be rejected is to do with the intensity of the light. What we actually observed is shining metal surface with light will eject electrons, but we get nothing with red. Nothing. How could we get nothing? But high wavelengths of electrons, so blue light, always came off at the same speed. I does not matter. Having a bigger intensity doesn't get us any higher energy electrons. It gets us more of them, but they're all at the same energy. What gives? Even so, intensity doesn't matter. Electrons are all at the same speed. So what gives? So we have to have this idea of this cutoff frequency. We have to have some minimum frequency for these electrons to pop off, and then the maximum kinetic energy of these emitted electrons is independent of I, which is crazy. The maximum kinetic energy of the photoelectrons increases with increasing light frequency, so the frequency is what's important. And electrons emitted from the surface are almost instantaneously, even at low intensities. So we can just send one little photon of blue light and pop off an electron. It's crazy. So the problems were that the effect is no effect is observed below some cutoff frequency, that we have some sort of minimum. The maximum kinetic energy depends only on the frequency and not intensity. The maximum kinetic energy increases with increasing frequency, and the effect is instantaneous. There's a 1-1 relationship. I can send one photon and get one electron. So Einstein's explanation was that light was a packet of energy called a photon. So this brought back Newton's theory that we have corpuscles of light and would be emitted even when a quantized oscillator jumped from one energy level to another. And this we now know are electrons and the orbitals within the atom. So he extended Planck's idea of quantization now to electromagnetic radiation. And the energy of the photon should look familiar as HF. We put an N in here in the last section. And even a photon can give all of its energy to an electron. So basically the photon gets completely absorbed in this process. It's obliterated. The maximum kinetic energy of the liberated electron is equal to HF, the energy from the photon, minus whatever cutoff energy that we needed to have. So this is the cutoff frequency. This is basically the energy we need to just make it happen, and this is the energy that's left over, gives us our kinetic energy. So in experiments, we found that the kinetic energy is a function of the frequency, where we have this cutoff frequency. The photoelectric effect then can be explained using quantum mechanics and not classical mechanics. So classical mechanics, whether electrons are ejected depends on the intensity of light. But quantum mechanics, we know it's the frequency. The kinetic energy is based on the intensity of light, is what we thought, but it's actually the frequency. You notice that it's frequency. That we figured that in looking at this system in a classical mechanical way, it's only a matter of time. It's not. You have to have the right frequency. This proves the duality of light, that light is a particle. So what is this cutoff frequency? Each different metal has a different cutoff frequency because the electrons have different binding energies to the nucleus. This cutoff frequency is given by this. Lambda c is equal to that Planck's constant times c divided by this phi value that is defined on the metal. So these are given at tables. Each metal has a different phi value. In this problem, we have two 200-watt lasers, one with red, infrared really, and one ultraviolet. So just below our visible spectrum and just above our visible spectrum. First question is which photons have greater energy? We should be able to not really think too much and figure this out. The ultraviolets are going to have more energy. But if we look at our formula, the energy is equal to HF, or H times C over lambda. The one with the smaller c, so smaller lambda means energy is bigger. So our ultraviolet light is going to have more energy. Now the problem asks us to figure out what those actual energies are. So we'll start out with the red. E is equal to H is 6.63 times 10 to the negative 34th joule seconds, times C is 3 times 10 to the 8th meters per second, and divide that by that wavelength 2.0 times 10 to the negative 6 meters, gives us a value of 9.95 times 10 to the negative 20th joule seconds, or 0.62 electron volts. And we can do the same thing then with purple and find that it has considerably more energy at 18 electron volts. Now we're going to look at silver. What happens to silver when we shine these lights on it? We know that this is the work function for silver, and we want to figure out what the kinetic energy is of the electrons leaving. The kinetic energy is again HF minus phi, and we've figured out what HF was for each one of these. This is HF, and this is HF for purple or ultraviolet. Then we'll figure out, so for red, we have 0.62 minus 4.3. I can write a 0, is not possible. We can get a negative number. We cannot have a negative kinetic energy, so red is below the cutoff frequency, and that's not going to happen. For violet or ultraviolet, so infrared and ultraviolet, we have now 18 electron volts minus 4.3 electron volts gives us 13.7 electron volts, which will then be the kinetic energy. Now we're going to look at using those same formulas to figure out what the cutoff frequency for silver was. We said the work function for silver is this number, and we know this is a relationship. So we're going to say that the minimum value for the kinetic energy is going to be equal to 0. This is, again, the maximum possible energy that the electron could come off with, not the minimum. So we're going to say that at 0, we're going to just barely hop this electron off. That means HF is equal to lambda, and then that means F, what we want to solve for, is equal then to phi over H. We have all those numbers now. So phi again is that 6.89 times 10 to the negative 19th joules based on a material, and Planck's constant again is 6.63 times 10 to the negative 34th joule seconds. And you'll notice these joules cancel out, so we get units of 1/seconds, or hertz, and that gives us 1.04 times 10 to the 15th hertz.